This is a video for section 1.5, Math 120. We're talking about exponential functions in this section, so we're going to go through quite a few of the properties of exponential functions. So, an exponential function is not an x to the fifth. That's a polynomial. It could be if it's to the fifth. It's not a polynomial if this was 5.5. So that would be called a power function if it was x to the 5.5. An exponential function has a base of a number and it's raised to an x power. Now this will now be the inside, so for considering shifts, these are the shifts we'd be looking at, and I recommend you pause this right now. I'm going to come back to this in just a couple of minutes. Pause this, write this down, see if you can figure out what these are, and then I'll come back to those once we've looked at a few other things here. Some of you have purchased the textbook, so you could go into the textbook and take a look through 1.5, and I recommend it if you purchase a textbook. Just reminding you, if you didn't, then you might want to look at the individual PowerPoints that I have for you. So if you go to your course, in the modules, the first one, the Test 1 assignment, Test 1 resources, I want the PowerPoint for 1.5. I'm making that video right now, which is why it's not available. The rest of them are available, and by the way, here's the 120 playlist, so if you didn't want to go into these individually, you could just make a link to the 120 playlist so that you'll be able to see these videos. They're organized so that the last one I made is on the top. The calculator for the calculator emulator for the computer is here if you want to follow those instructions. And then I have a new note file in Google Docs also. So let me go down to PowerPoint 1.5. If I touch this, it's going to open up the PowerPoint here, which is fine with me because I don't really care what it looks like. But you might want to download it, and you can do that with the little download button, and then you can play it at your leisure on your computer. In here it's talking about the exponential functions, and then it's talking about some exponential rules that you have. So here a to the negative 1 is of course 1 over a to the, this should say 1 there, it shouldn't say n, this should be negative n, so there's a typo in there. So be aware when there's a typo. The exponential functions are showing what they look like here. They grow from above the x-axis always, so the domain does not include 0, but it's from 0 to infinity. The range does not include 0, but it is from 0 to infinity, parentheses 0 to infinity. The domain is all reals. You can put any x into an exponential function, as long as the base is positive. The base does need to be positive. There's some other things on this that you look through. Some of you may need to go back and understand where square roots are in terms of where they are on the number line. You might want to look at some other exponential properties here. So it shows you some exponential graphs. Shows you all the different ways that you need to be looking at the exponential functions. In particular down here, the exponential functions, it does remind you of the laws of exponents. So that might be a pretty good slide to look at. There are other shifts and stretches here, so you might want to take a look through there. Most of you, I hope, are using this. So if you're downloading and using these, it's to your advantage. So going back through what I initially said, exponential versus power, I want to graph these on my calculator and be able to see them a little more clearly. Some of these are really high power, so they end up really strange on your calculator quickly. And you also want to be able to find things like intersections of these graphs. So you want to be able to find where x to the fifth intersects 5 to the x. So first of all, let's look at the shifts, and then we'll look at the graphs themselves. If I shift right 2, that means that in here, 5 to the x, I want to put it in with the x, and remember we'll do a negative 2 here, so this would be 5 to the x minus 2. If I shift up 4, 5 to the x is my graph, up 4 is going to be written on the outside because it's vertical. A horizontal shrink of 1/5 goes in with the x, so we'll have 5. A shrink of 1/5 would be to the 5x. And then a reflection, because whenever we have a shrink, we do the opposite. So that's multiplying by the reciprocal. In this case, we're multiplying by the reciprocal would be the opposite. A vertical reflection is on the outside, so negative 5 to the x is what we would do for the graph there. You can graph these and make sure that they actually do what we said they did. If I'm looking at domains and ranges here, the domains for all these are all reals. And you can simply write all reals like this. 2 lines and then the rest of the r. The range for these varies. This didn't shift up or down, so there's no change in the range. So the range will be from parentheses 0 to infinity. This one shifts up 4, so it's going to start at 4, but it doesn't include 4. So it'll be 4 to infinity. This one is just a horizontal shrink, so that doesn't change the range from the original graph. So that's just 0 to infinity. Not on this graph anyway. We saw some online in 1.4 that it did change because the domain was very small and shifting it or shrinking it would make a change in the domain. So this is on negative on the outside. It's a vertical reflection, so that means we're going to be going, instead of doing a graph that looks like this, the vertical reflection would be a graph that looks like this. So our range would be from negative infinity to 0. And it's important that you do not write this backwards, because negative infinity is before 0, and this interval notation is written in the order that it appears on the number line. Now I do want to go back and actually graph these on the calculator, see what they look like. So turn my calculator on. I got x to the 5th and 5 to the x in here. If I just do a zoom 6, that puts it in my standard grid. And it may not be very helpful because I can't really see much here. Zoom 6, and it takes off exponentially. Now I know that when this is 5 to the 5th and this is 5 to the 5th, that they're actually going to cross. So I could put in here a y value. So I'm going to go to my window and put in a y value of a y max of 5 to the 5th. And I don't know what that is. So 5 to the 5th is what I'll put in. And I'll put plus 1 just because. So we'll hit graph, and we should be able to see the graph. Note that it's really, really small below because this is going from negative 10 to 5 to the 5th. And I don't know what that is. But I can see that now I've got a couple of places where this graph crosses. Now this isn't the easiest way to see where we have these graphs crossing. I could find the intersection here without any problem, but I can see there's another place it crosses too, and there might actually be a third place it crosses. It does definitely for a x to the 2nd and a 2 to the x. So if this was a 2 instead and the exponent here and the base here, then I would be looking at a graph that crosses 3 times. But this is 5 to the x, so it probably only crosses twice. So instead of doing this, if I wanted to find the intersections, y equals, I might do instead x to the 5th minus 5 to the x. So I'll put both the graphs in the same place. And now I'm looking at the difference between them. So where they cross will be what makes this 0. So where they were the same when I had them individually like this would be what, if they're difference, if I took the difference, would make them 0. So I'm going to do a zoom 6 again so I can see this. It might still be difficult to see, but we'll adjust the window a little bit so we can see it. So there's what the graph looks like, and I can really clearly now see where these are 0. So if you want to find intersections of graphs, sometimes it's difficult to set the graph up, but here if I do their difference, the difference of the two graphs, I can see where they cross pretty easily. It doesn't look like they're intersecting because I did do, instead, let me write this down. Instead we're going to do x to the 5th minus 5 to the x equals 0. So that's what we did on the calculator to figure out where the intersections were. So this is for intersections. So if you want to see where a graph intersects, sometimes it's easy to see it on a graph, just straight up the way you're looking at it, but sometimes it isn't. And some of these numbers will get really big really fast. On homework 1.5, looking at the first problem, this is an x to the 8th and 8 to the x. So they're asking you the same kind of questions I just went over. So carefully look at the with an 8 to x, maybe following through the same procedures that they did. And you may have 5s here. So there's they tell you a viewing rectangle to look at, and there's also a video example if you want to look at the video example there. The second graph here has an e to the negative x, so let me show you where that is on our calculator. So if I wanted an e to the x, I'm going to go into y equals, I'm going to clear this out. The e is down here above the ln, so you'd have to hit the second key to get to it. Or you could use the e over here. See where pi is? The number e is right above the divided by on your calculator. So that would give you an e, and then you have to put the caret to get the exponent. This one gives you the e to the x automatically. So second ln e to the x here And I'm going to do zoom 6 again so that I can see it. It looks like any other of the exponential functions. E has a particular number, so we'll look at what E actually is. And I could look at the table to see this. The number E is 2.718. It's a non-repeating decimal number, and it's actually a limit. We'll talk about it later when we're using limits. So you should know automatically what's going on here because we've been studying shifts. The 1/4 is a particular kind of shift. The negative here is a particular kind of shift. And then the -3 on the outside is a particular kind. So they're asking you to go through those shifts. It should not be difficult for you. If it is, please see me during office hours or right after class will be fine. A few of you have asked for time right after class. So we could actually get on and do a few more examples then. For the problem number 3 here, they want me to use the laws of exponents to rewrite and simplify the expression. So 4 to the -3 and 2 to the -8, these bases have to be the same, so I'd have to rewrite these. And then there's a rule about how to rewrite this in terms of exponents. Notice it's in the denominator, it has a power, and it has a root. So you should be able to write that in one little expression. So let's do an example like that. Not the same one, but an example like it. So before we can simplify this, I have to make these have the same base. And what I see very clearly is that 25 would be 5 to the second, and 5 would have the same base then. So I can rewrite this as 5 to the second to the -4th over 5 to the -3rd. So this is the same as writing 5 to the -8, because we have two exponents like this we multiply, over 5 to the -3rd. Now I could go ahead and reduce this by doing the subtraction, that'd be fine, or I could flip both these things and then do the subtraction, it really doesn't matter. So this would be 5 to the -8 minus a -3, which is 5 to the -8 plus 3 would be the -5th, which is the same as 1 over 5 to the 5th. Now when they ask you to do this, they may actually want that number. So if I do 1 divided by 5 to the 5th, I get this. So math, enter. Get 1 over 31/25. So that would be my answer. Now, you're looking at this going, I really could have just put this in my calculator to begin with. 25 to the -4th divided by 5 to the -3rd. And you can, but you want to be aware of how you could check your work if on the calculator, but it's not necessary to check my work. And then math, enter, turns it into a fraction. So if I ask you to show work, this is what I would expect. I don't often ask for work like this because this is a pre-calculus concept, but it does help you to understand, if you work through this a couple more times, exactly what you should be thinking the answer should be when you get done. Now this one I can't do on my calculator. This one is really just rewriting it. And let me go back to the problem so that you can see. It's asking you rewrite and simplify the expression. It doesn't say whether or not they want negative exponents. So you might try a negative exponent and then it might not work and you'd have to come back and do it without the negative exponent. So here, if I have 1 over the 7th root of y to the 5th, that gives me 1 over y to the 5/7, which would be a good answer. This is also the same as writing y to the -5/7. 1 over a number to a power is the same as the number to a negative of the same power. So all you're doing is changing the sign. This means that this is in the wrong place. It really ought to be in the denominator. One of these is going to work correctly. Remember, you have 5 times at trying these, so you should be able to get these on the 2nd or 3rd try. If you're having trouble beyond that, you should see me. For the next part, you should refer back to the notes you have for a previous problem on this exercise set. We used a base of 5 when we were talking domains and ranges, and the textbook used a base of 2. On number 5, there are a couple in part A that are obviously wrong, so be careful that you don't select one of those. We've already said what the approximate value was. I'll show you how to find that, and we also know what the natural exponential function looks like. So they're telling you what 2 to the x would look like in number 6. 2 to the x is the blue graph here. And they want to know what happens for these particular changes in the graph, the shifts, the transformations. So before this is outside, so that's a vertical, and the negative means reflection. Inside here, that's horizontal, in with the x, and the negative means reflection. So this is going to be reflected vertically, so it's going to spin this way, and it's also going to be reflected horizontally, so it's going to go down across the x-axis also. Note that it says do not use a calculator, but I'm not going to take your calculator away from you during the test, so you could actually use a calculator here. We already did an example of this previously in this video, so this is just using the E instead. You should be able to do the shifts just like this. I will expect you to do it on the first test. From section 1.4, I believe, we talked about the domain of compositions of functions. So the e to the negative t is a nice function, domain is all reals, and the sine is a nice function, domain is all reals. So you should be able to determine easily what this is based on what you did in a previous video. The square root graph is not quite so nice, so you might actually put this in your calculator, see what this looks like. On number 9, you're actually going to put the 3 and 32 into this function, and you'll have a function with 2 equations, 2 unknowns, and you'll solve for that c and the a. So that's a little bit of algebra there. Let me know if you need help with it. When I was a little girl, maybe about 10, I have an Uncle Jim that ran a big farm out in Iowa. He's still alive. He's in his late 80s. I'm close to 90 now. But he asked me this. He asked me this exact question here. So I left this one in because I thought it was an interesting one to do. I've already compared x to the 5th and phi to the x and showed you how to find those intersections. So that one's been done. For number 12, you might use the trick that we want e to the x minus 100 million is greater than 0, and see if you can find that answer pretty easily on your graph. I'm going to show you the steps for e to the x minus 1000. So if I do this, I do a zoom 6. I'm not sure what it's going to look like. I'm interested in where it's greater than 0, so where the graph is above the x-axis. e to the x minus 1000. So I can see that before it's going to be above, I might need to get my window so that I can see the y values better. So the y values might start at negative 10 is fine, and I'll make this 100 to see if that works. So graph it again. I might be able to see a little better what was happening to this graph. But it still looks like it's going straight up, and I can't really tell much at all. If I look at the table, second table, these are negative values, so it looks like around 7 is when it changes and it becomes positive. So I want it greater than that, but that's the value I need to put in for when is e to the x greater than 1000. So looking at the graph again, I just want this x-intercept here, which is a 0. So I do second and then calculate. I want the 0, which is 2. It's going to ask me for left bound. I know it's between, what was it, 6 and 7? 1, 2, 3, 4, 5, 6, 7, and 8, I guess. Well, I know it's between 5 and 9. So I can see that I'm looking in here. I want to guess. It really doesn't matter what I put in for the guess. So I'll just put enter. And it says the 0 is at 6.9077553. So you're going to do those same steps with e to the x is greater than whichever number you have in here. Same steps. Number 13 is about exponential growth. So we're looking at exponential functions. Bacterial culture starts with 900 bacteria and doubles in size every half hour. So that means that 900 times 2 would be 1800 is what happens a half an hour from now. So I could continue that process for the 3 hours, which means I do 900 times 2 times 2 times 2 times 2. So we'd end up with 3 hours later. Need to put enough 2's in. So if we have 900 times 2 to the 3 hours later would be 2 to the 6. To the 6. That's what we'd have for our answer there. So whatever that ends up being. So what would we do for an equation here? This is saying how many bacteria, and they're only wanting the right side of the equation. Notice the variable is t. So let's think about this a second. It says that we start with 900 and we double, multiply by 2 every half hour. So with my 900, I did times 2 to the 6 is what I ended up with. That was actually 3 times 2 though, right? Or 2 times 3. So if this was for any amount of hours, the only thing that would change there would be the 3. So think about how you might write that as a formula, as an expression. Notice here that the t is the variable. That's a big hint for you. Don't make it a capital T. A little lowercase is what they're looking for. How many bacteria are there? 40 minutes. Well, once you have this formula, you're going to need 40 minutes is how many parts of a half an hour? Well, it's how many parts of an hour, rather. So that'd be 4/6 of an hour. So you'd have to put t equals 4/6 then. And graph the population function, estimate the time for the population to reach 40,000. So that goes back to what we did in the previous problem. We want to know when e to the x minus 40,000 is 0 is one of the ways that you could do that. Number 14 is really just interested in whether or not you can divide by e to the x, which means is it ever 0? So think about the domain of any of the exponential functions, and that'll be an easy answer for you. That concludes 1.5. We'll talk about any questions you have in class. Please come see me in office hours or make an appointment if you're having any issues with these exercises at all. You have 5 times a piece, except for these. I don't think you get 5 times to answer.